unit. So, as an electronics and communication engineer, we need to know certain basic concepts which make us an communication engineer. So, one of them is satellite communication. So, in satellite communication, we should be familiar with these concepts. So, the first concept is your orbiting. So, this orbiting is obtained from Kepler's law with the help of Newton's law. We are going to see what is an orbit, what are the orbital parameters, what are the orbital perturbations, what is station keeping. We are going to see geostationary orbits and non-geostationary orbits. What are they? We are going to see about the look angle determination and the limits of visibility during an eclipse, followed by subsatellite point and the sun transit outage. Then we'll be seeing the launching procedures of a satellite into space, followed by launch vehicles and propulsion. So these are the contents of unit 1 and in this presentation also. So first let us see what is an orbit. So as you all are familiar with the orbital structures of space and earth, so when two bodies with a difference in mass, so assume that an higher mass and the outer is having a lower mass. So two bodies, whether it could be celestial bodies, whether it could be planets, whether it could be satellites, anything, as you have seen in the Pluto Charon system. Okay, so two bodies with a difference in mass orbiting a common barycenter, which is external to both the bodies, can be defined as an orbit. You can see plus in the center of this circle, and we have two bodies orbiting around them, heavier mass, another is lighter mass. So two bodies with a difference in mass orbiting a common barycenter. Example is your Pluto Charon system. So this is an orbit. So next, two bodies with the same mass orbiting a common barycenter. Is this example? We have two bodies of equal masses with a barycenter in the middle plus, and these are revolving around it. So which is similar to your 90 Antio system. This is also an orbit. So I'll show you next diagram. Two bodies with a major difference in masses orbiting a common barycenter internally. Okay, internally. You can see that these two, which are shown in the previous, are external. So you can see that it is externally revolving. Whereas in this diagram, the two bodies are having a major difference, orbiting a common barycenter, but one body is internal. You can see that we have a barycenter at the center. One body is revolving within the center, another body is outside the externally. Okay, so this is a fashion similar to Earth and Moon system. Okay, so Earth is revolving around Sun and Moon is revolving around the Earth. So always we are familiar that Moon is having a lower mass compared to Earth. Okay, so this is an example of Earth Moon system. So next, difference in mass orbiting a common barycenter internal to a single body. You can see that we have a barycenter at the center, and mass is present, which is exactly present within the barycenter internally, and another body is revolving that barycenter as well as this internal body. So this can be given as an example for a Sun-Earth system. So similar to the Sun and Earth system, this resembles as an example of an orbit. So this is also an orbit. So next, two bodies with the same orbiting having a common barycenter with eccentricity elliptic orbits. This is also an orbit. So you can see that at the center we have a barycenter. Two bodies with equal masses are revolving around this barycenter. So this is also an orbit. So you can see the definitions, or you can see the examples of all this in a single pictorial representation of satellite. Sorry, pictorial representation of an orbit. All the four diagrams. Okay. So this is what an orbit is. So coming to the first topic is Kepler's law. So Kepler's law stands as a basic for any bodies which are being revolving around any other bodies. Okay. So Kepler's law of planetary motion is given in three different laws. One is Kepler's law 1 or Kepler's first law, Kepler's law 2 or Kepler's second law, Kepler's law 3 or Kepler's third law. So this I had given you in terms of points. So the first law states that the orbit of any smaller body about a larger body is always an ellipse, with the center of mass of the larger body as one of the two focus or foci. So the meaning is that the orbit of any smaller body about a larger body is always an ellipse. So if you see the structure, for example, we take two bodies. A larger body is present in the center, as in this case, a larger body is present in the center, and another body is which is smaller compared to the center body will revolve around the orbit in an elliptical fashion, or it takes a shape structure of ellipse. So that is what Kepler's first law is. The orbit of any smaller body about a larger body is always an ellipse. So this is Kepler's first law. Second law is that the orbit of a smaller body sweeps out equal areas in equal time. The orbit of smaller body, when it revolves around the larger body, takes equal areas in equal time. So this is your The area of coverage of the smaller body, how it revolves around the larger body, will have or will cover equal area with equal time. So this is Kepler's second law. So let us move on to the area coverage. You can see we have sun in the center, and smaller bodies revolving around that area. You can see that the direction, right, from P1, P2, P3, P4, P5, the bodies. So here the bodies I taken example as planets. So the planets are revolving around the sun. Okay. So planet P1 moves to P2 in a particular time of T. Okay. So in the same case, planet P3 or P4 moves and covers the same area with the same time. Okay. Planet moves from period 1 to period 2 in a particular time, and it covers some dimension areas. So that will be equal to the same planet moving from period 3 to period 4 within the same time. Both the areas will be equal. So this is your Kepler's second law. I think from this diagram you would have understood Kepler's second law. Okay. I'm keeping the sun as your center and planets are moving. So the area covered by planet 1 at a particular time within the specified time will be equal to the planet moving from other points within the same time. For example, you are taking 24 hours, 24 hours for uh, point P1 to P2. That area coverage is equal to point area coverage of P3 to P4 for 24 hours. This is what Kepler's second law is. So this is an example of a satellite which is revolving around Earth. So the satellite is a body with lesser or smaller mass, and Earth is a body which is having larger mass as compared to satellite. So whenever the satellite revolves around the Earth, it takes elliptical path. Okay, so and the area of coverage as I had shown here. So when this revolves also for a specified time, when the satellite revolves around the Earth, for example, if it revolves for 24 hours, the area of coverage at one point for 24 hours and the area of coverage at the other point for 24 hours would be same according to Kepler's second law. So this is what the diagram is. So this satellite is orbiting around the Earth. So next is Kepler's third law. So the Kepler's third law states that the square of period of revolution of a smaller body about a larger body is equal to a constant. It is equal to always a constant multiplied by the third power of semi-major axis of the orbital ellipse. Okay, keep in mind. So when this smaller body, which we call as satellite, when it revolves around the larger body Earth, will take some duration or it will have some period of revolution. So that period of revolution about the larger body will be equal to a constant. So constant is mu. So 4 pi square by mu into the third power of the semi-major axis of orbital ellipse. So semi-major axis will be seeing the definition in the orbital parameters. What is an semi-major axis is for an ellipse. So this period of revolution. So for example, if it takes one period of revolution, if it completes, if the satellite moves around the Earth from the starting position and it comes back to the starting position again, making one revolution, would be equal to t square, which is square of period of revolution. T square is equal to 4 pi square by mu, which is the constant, into a cube, which is the semi-major axis, third power of semi-major axis. So this is your Kepler's third law. Okay. So this equation determines the period of any satellite. So how many revolutions can a satellite make can be easily determined by this equation. And by using this equation, it would be very useful for every GPS receiver in calculating the position of GPS satellites. Okay. A short description of this Kepler's law. Okay. Johannes Kepler developed these three laws which describe the motion of the planets across the sky. So what I had said, the first law deals with the orbits. All planets move in elliptical orbit with the sun at one focus. Second, law of areas. A line that connects a planet to the sun sweeps out equal areas in equal time. Okay. And law of periods. The square of the period of any planet is proportional to the cube of the semi-major axis of its orbit. Okay, it is proportional. So this is what Kepler's law is. We'll see this law of orbits. Okay. So any queries, type in chat box. If you have any queries, please type in chat box. Okay, since there are no queries in the chat box, we'll move further to the law of orbits. So the law of orbits can be diagrammatically represented as such with respect to sun. So sun is your larger mass body, and around the sun the planets are revolving. You can see, for example, sun is at the center, just inside, and the planets or satellites which revolve around the orbits which are in smaller mass bodies, so they take elliptical shape structure. So the center I am marking it as some point with dot. Okay, and from the external point of the ellipse or the edges of the ellipse to the center which I defined is your semi-major axis of the ellipse. Okay, the external point represents is the farthest point. You can see that if I take the center of the ellipse, you will be having two external points. One point is nearest. So this point which I am showing at the top is nearest. At the bottom which I am showing is nearest. So the longest or the farthest point from that point we call it as perihelion. The perihelion. So the longest point is called as perihelion. So from there to the center, we mark a point. So that measured value is semi-major axis of the ellipse. Okay, semi-major axis of ellipse. So it is represented as A. Okay, and if sun is present, if sun is present in between this, okay, keep in mind sun revolving is different, and the satellite or the planet revolving is different. So the planets will revolve around the sun in this elliptical fashion, and the planet's revolution from the center it takes shortest path, and from the center it takes longest path. So from the longest path to the center is called a semi-major axis of ellipse A. Okay. So when this planet revolves around the sun, the sun is obviously present inside that. So from the center to the point of the sun is taken as EA. E is your eccentricity. E is your eccentricity of the ellipse. E is your eccentricity. And the distance from the sun to the farthest point is RP, measurement RP, and from that sun's point to the longest measurement till this point. You can see from the diagram from this point to till this point from the other end is denoted as RA. Okay. So what is this is that the focus of the planet with respect to sun. Okay. So how do I calculate RA is that RA can be calculated by semi-major axis into 1 plus eccentricity E, and RP can be calculated as A into 1 minus A is your semi-major axis. A into 1 minus E is the eccentricity of ellipse. So this is your law of orbits. With a diagrammatic representation. Next, the law of areas. So consider sun is present at the center, Planets are revolving at different time periods. I have marked in some colors. So these dots, the black color is your sun, assume it, and the violet color are the points of a particular planet which is revolving around the sun. So some, for example, period P1 to P2, P3 to P4, P4 to P5. The time duration can be depending upon the measurement. And if I put lines, okay, a line that connects the planet to the sun sweeps out equal areas in equal times. For example, I'm taking it for 48 hours. The 48 hours, I make a measurement. The area covered at 48 hours by a planet will be equal to the area covered by the same planet in the other side or in the opposite side for the same 48 hours. So area of coverage will be same. So this is your law of areas or Kepler's second law. Next is your angular momentum of a particle. So the angular momentum is the same at every point on an orbit. When it is closer, its speed increases. So which can be measured by Kepler's law. So the angular moment of a particle of a mass m. So m is your mass of the body which is revolving around in an orbit. So with respect to a chosen origin, the value can be found out as L is equal to mvr sin theta. So r is the distance between the sun, which is at the center that we are taking, and the planet that is in motion in your elliptical path. The planet which is in motion, okay, which is moving around the sun. So that center to the planet's elliptical path is measured as r. So we take r it is. So mass is your m. Okay. So then we can find the vector product of it as L is equal to r into p. So where p is equal to m v, mass into velocity. So by using the Fleming's right hand rule, where L is the direction of out of the diagram, we can find L value as mv r, mass into velocity into radius, sorry, not radius, the distance between the sun and the planet being measured. Okay. So which gives us law of period. So here is an graphical representation. A graph has been drawn. In x-axis we have square of the orbital periods in years, and in y-axis we have a cube of semi-major axis, which is a cube. Okay, so with respect to all the planets, it is being given: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Newton, Pluto. So the square of the orbital period takes these many years. Square of the orbital period. So the straight line which is given represents the Kepler's law of periods for every revolution. You can find it here. Okay. T is your computation which is being calculated with respect to Earth period, Earth years. Because we all are manipulating only with respect to Earth, because mankind has been defining all those things. So with respect to the computation of the Earth, it is being calculated. So T is Earth years, A cube is your astronomical units, which is measured for semi-major axis of the Earth that we are going to find, and constant mu we had wrote, right? So mu is your GM, which is solar masses, where 4 by pi square by G will be always 1 and mu differs. So simply the period of revolution can be measured, or it is proportional to A cube. Okay. So this is the law of period, Kepler's third law. Next topic is perfectly geostationary orbits. A perfectly geostationary orbit must have eccentricity is equal to 0. It must be at correct altitude, having the correct period. It must be in a plane of equator, having 0 indication with respect to equator. Okay. So before starting this geostationary orbit, we should be familiar with three different terminologies. One is latitude, longitude, and altitude. So in that latitude, you all are familiar. Longitude, also you all are familiar. So what is altitude? Altitude represents the measurement of the distance from the Earth's surface to the space. So if all these three conditions are satisfied, they are called as perfectly geostationary orbits. Eccentricity 0, having correct time period or the correct altitude, and having 0 inclination with equator of the Earth. So what happens if inclination or eccentricity is not 0? The answer is the satellite will be in geosynchronous orbit. You can see that geostationary and geosynchronous. Geostationary is a term called, if the eccentricity is 0, we call it as perfectly geostationary, which is being stationed at a particular point in space. And if it is not so, the orbital period, though it is same, the satellite will go into geosynchronous. So next is an example. I'm going to show you an example of the two different terms. One is apogee, second one perigee. Consider two bodies. One body is having a larger mass, another body is having a smaller mass. Okay, so in this case, I'm going to take Earth as your larger mass and a satellite as your smaller mass. So the smaller mass will always revolve around the larger mass. So the satellite will revolve around Earth in an elliptical fashion. So when a satellite takes an elliptical fashion revolving around the Earth, it will have two different points. One is the satellite being present nearest or closest to the Earth, which is mentioned here. I can show you it in the left side diagram. So the satellite is present very closer to the Earth. So this distance, or the nearest point, or the nearest distance from the Earth's surface to the satellite is called as perigee, as shown in the diagram. And since the satellite is revolving, it will go to the farthest point. It will go to the farthest point. So this point, whichever is present, from the Earth's surface to the position of the satellite at the farthest point, is called as apogee. So these are the definitions: apogee and perigee. So when a satellite revolves around the Earth, the satellite will be very much closer to the Earth's surface at a point. So that point is perigee, and the satellite will be very much farther away from the Earth. So that point is apogee. So apogee and perigee, two different definitions. So the definitions which I told you is being given here. Apogee is the point in the orbit where satellite is farthest from the Earth. Perigee is the point in the orbit where the satellite is closest to the Earth. Always the perigee and apogee will be opposite to each other, and they had calculated the orbital period of a GEO, geosynchronous satellite, as 23 hours, 56 minutes, and 4.1 seconds, which is one sidereal day. So you may ask, what is the sidereal day? Sidereal day is that 24 hours. And sidereal day is 24 hours. So the solar day is 3.4, which is measurement of the geosynchronous. 3.94 minutes longer than sidereal day. Okay. So next is the representation of the orbital shape and size parameters. The semi-major axis. In the previous diagram, I had shown the perigee was at the left side and apogee was at the right side. So now I'm showing perigee at the right side and apogee at the left side, such that why I'm showing like this is that the Earth is also revolving by its own axis, and with respect to that, the satellite also revolves. So in any direction, the apogee may come, and in any direction, perigee may also come for a specific satellite. So that I should make you understand. So that's what I had shown you. There in left side and here in right side, perigee. There in left side, right side apogee, here in left side apogee. Okay. So this is the diagram. Orbital shape and size parameters. Now let us see the terminologies. So semi-major axis. The semi-major axis is half the distance between the 2 points in orbit that are farthest apart. You can see farthest points are your apogee. So half of that is your semi-major axis. Then apogee or perigee radius. So the apogee or the perigee radius can be calculated by measuring the center of the Earth to the points of maximum for apogee and points of minimum to perigee. So which we can equally define for apogee radius and perigee radius. So next is the apogee altitude or the perigee altitude. So the apogee altitude can be measured from the surface of the Earth to the points of maximum radius, whereas perigee can be measured from the surface of the Earth with minimum radius in the orbit. So maximum points are your apogee, minimum points are your perigee. So from the surface of the Earth, if you measure the altitude, so that gives your measurement of altitude for apogee to as maximum, and whenever it is minimum, it gives your perigee altitude. So next is period. So period is defined as the duration of one orbit the duration of one orbit based on assuming two body motion is period. So when a satellite starts revolving around the Earth, it starts revolving and it comes back to the original position. Okay, so that entire duration or the entire revolution is called as one period. Next is mean motion. Mean motion is the angular speed required for a body to complete one orbit. Angular speed. So the speed at which the satellite takes or the satellite moves to complete one orbit. Okay, generally it takes for one solar day we compute it as 86400 seconds or 24 hours. Okay, which is equal to 1 day. So for 1 day it takes this many seconds to as your mean motion considering two body motion. So two body motion is a simple that satellite revolving around a earth or a smaller body revolving a larger body. Whatever might be, it could be an artificial satellite or it could be a natural satellite. Okay, it doesn't matter. We compute it for 24 hours or 86,400 seconds. Next parameter is eccentricity. Eccentricity. The shape of the ellipse. The shape of the ellipse when it becomes zero. Okay. The shape of the ellipse having eccentricity 0, then it is a perfect circle. And if the eccentricity is 1, then it is a parabolic fashion. The shape of the ellipse comprising the orbit ranges between a perfect circle. So which is eccentricity will range between 0 and 1. If it is 0, it is a perfect circle. If it is maximum 1, it is a parabola or it is a parabolic fashion. So this is your size orbit. Size orbit's eccentricity. Next is look angle determination. Okay. So the surface of the earth is divided up into grid-like structures. As I said earlier, terminologies, latitude and longitude. So though you would have studied latitude and longitude earlier, some of them are not familiar. What is this latitude? How do I measure whether it is east-west or whether it is north-south? Okay. So I'll give you the definition also now. Though you are familiar and though you are not familiar, you can make a note of this. Latitude is the angular distance measured in degrees, measuring from north pole to south pole of the earth. The earth we have, so the surface of the earth is can be divided into grid-like structures. We can draw imaginary lines or we are insist to draw imaginary lines. So these imaginary lines which are being measured from north to south, okay, like from top to bottom, measured in degrees, is called as latitude. And if the angular distance is measured in degrees from west to east, I forgot to type it, so typing. Okay, so it is west to east, measured in degrees from a given referenced longitudinal line. Okay, gives you longitude values. For example, latitude 90 degree north is 90 degrees. So this is how look angle determination starts with latitude, longitude. I can show you here latitude and longitude on the globe. Okay, so the earth is divided into grid-like surface structures by imaginary lines of latitude and longitude for determining positioning. Okay, so from top to bottom, imaginary lines are drawn, which is north to west, and in the center we draw it in the center from top to bottom, given as 0 degree, which is Greenwich meridian time. The time measured at 0 degree latitude is your Greenwich meridian time, GMT, we call it in short. Okay. Then in longitude, we divide into two halves first, where in longitude we can see which runs from center 0 degree, which we call as equator. Equator is the center which divides the globe into northern hemisphere and southern hemisphere. Okay, 0 degree. You can see that this goes across the continent Africa, which is at the center. Okay. So this globe you can see at the center we have an equator running from west to east, which is passing through the continent Africa and South America. Okay, and which is your longitude? We have degrees of measurement: 15 degree, 30 degree, 45 degree, 60 degree, 75, 90. Okay, in longitude. So the center is your prime meridian. Prime meridian. Okay. So this diagram is to show as how the imaginary lines are drawn on the globe. Okay, latitude and longitude. Now let us see how this look angles comes into picture. Okay. So the coordinates to which an Earth station antenna must be pointed to communicate with a satellite are called look angles. Okay. So the coordinates represents x comma y coordinate or the latitude longitude coordinate always present on the surface of the earth. There will be an antenna which is used to communicate with the satellite. The satellite will be present in space, and all those I'll come in brief how these are being done in the next chapter or in the next presentation, where the satellites are being present, how they are being present, what is the distance between the satellites from the earth's surface, and how do they communicate, all we'll see. The time being we'll see the terminologies. Okay. So the coordinates to which an earth station antenna must be pointed to communicate with a satellite are called look angles. So these look angles are being commonly expressed as azimuth angle AZ or elevation angle EL. So what is this azimuth angle and elevation angle is? So the azimuth angle is measured eastward, which means clockwise. From geographic north to the projection of the satellite path. Okay. So we place a earth station or a earth antenna at the earth surface, and we are measuring clockwise direction. We measure it from clockwise direction from north position. Okay. So east north will be drawing a plane. Will be drawing a line to the projection of satellite path. Okay. So that is called as azimuth angle. Elevation angle is that the angle being measured upward from the local horizontal plane. Okay, drawing it from the earth horizontal plane to the satellite path is called as elevation angle. So if these two angles perfectly match, depending upon the satellite, the signals will be transmitted efficiently. So whenever we design a satellite, the look angles are to be determined carefully. So we should be familiar with azimuth angle and elevation angle. You can see it in diagram. You can see we have a satellite. We have a satellite in space. We see the representation of azimuthal angle as AZ. So from the north side to the projection of the path on the local horizontal plane, we move towards east direction. You can see that from north side we move towards east direction. So till the satellite's projection falls. So from the north direction to the east direction till it falls is called as azimuth angle. Okay, azimuth angle is measured from the true north in an eastward direction to the projection of satellite path onto the local horizontal plane. Whereas elevation angle is measured from the local horizontal plane with respect to Earth to the path of satellite. You can see that Earth is here. To the path of satellite, an angle is measured. So this we call it as elevation angle. So elevation angle and azimuth angle are your two basic look angle determinations. From this diagram you can see it. Let me see if yeah, a question by yeah. So how can we say that GEO is geosynchronous satellite. Geosynchronous. Okay. So geosynchronous satellites, Pavan, yeah. Geosynchronous satellites are the satellites which are having the orbital period. Okay, the orbital period as same as that of Earth's rotational period. So that we called as geosynchronous. So Earth's that satellite we called as geosynchronous satellites. When we design a satellite, and if that satellite is not having the rotational period as that of Earth, it is non-geo. It is non-geo. Yes, Pavan, is it audible? Yeah, the geosynchronous satellites are the satellites those are having the orbital period which is equal to the Earth's rotational period. If they are same, it is called as geosynchronous. So that type of satellites we called as geosynchronous satellites. Okay, thank you. Any other queries? If there is any other queries, you can put in chat box. Yeah, once again, azimuthal angle. Okay, right. Yeah, we are having two bodies. One is Earth body, another one is an satellite body. So the satellite body will revolve around the Earth. So the mass of the satellite is lesser than the Earth, which is having a higher mass body. So in this, after defining the latitude and longitude definitions, we are going to take two different look angles. One is azimuth angle, another one elevation angle. So the satellite is being placed in space. So from the space, we are finding the position of satellite. Okay. So with respect to that, I'll tell you in terms of altitude. Okay. So altitude is the measurement of the distance of the satellite from the Earth's surface. So that projected horizontally onto the Earth's surface. So projected. So by these dotted lines. Projected by dotted lines. So now from the Earth, take from northern direction. From north direction, from there move towards east. Okay, until this projected value falls on the horizontal plane along the earth surface, so that you mark it, and from the center of the earth put a point. Okay, so this angle which is being created from the north direction, which is n 90 degree, from there till this horizontal projection, is the angle which is being created is called as azimuth angle. And from this point to the path of the satellite, so this satellite will revolve in elliptical path. Okay, so this satellite will revolve in elliptical path in space. So put a point from the earth center to that path of satellite, connect the path of satellite by a dark line. Okay, so the angle between this path of the satellite and this projected from north side to east side is called as elevation angle. So in short, you can say that the elevation angle is measured upward from the local horizontal at earth station or the earth station antenna, and azimuth angle is measured from true north direction in an eastward direction to the projection of satellite path, which is falling on the local horizontal plane. If you if you see the earth segments, you'll be able to understand in a better way the details about satellite location in space and the earth space. Sorry, earth's satellite location. How the satellite is located in space, how it is being measured from earth surface with respect to antenna. Okay. Okay, fine. So next topic is sub-satellite point. The sub-satellite point is the location on the surface of the Earth that lies directly between the satellite and the center of the Earth. The center of the Earth is which we have defined as 0 latitude and 0 longitude. That is center of the Earth. And from where we are going to measure, okay, the location on the surface of the Earth could be at different points apart from 0 degree latitude and 0 degree longitude. Our measurement of antenna or the placing of antenna could be at different points. So that point can be measured by the subsatellite point, which is the location on the surface of the Earth that lies directly between satellite and center of the Earth. I'll show you that in the diagram. Okay. So it is the nadir pointing, NADIR, nadir pointing direction from satellite. So let us see. We have a satellite which is present in space. So the satellite, when it sees towards the center of the Earth, so that direction is nadir direction. And when from the center of the Earth, when you see towards the satellite, we call it as zenith direction. Okay, so let us see. So the line joining the satellite and the center of the Earth, C, I mark it as C here, center C, passes through the surface of the Earth at, at some points or some sub points. Okay, passes through the surface of the Earth at SUB, I consider it as SUB, which we call it as sub-satellite point. The satellite is directly overhead at this point, and so an observer at sub-satellite would see the satellite at zenith. So obviously the elevation angle will be of 90 degree. So when an observer or when an Earth station, one Earth station antenna is being put up, and when it is focusing towards the satellite in upward direction, we call that direction as zenith direction, usually at 90 degree elevation. Okay. So the pointing direction from the satellite to the sub-satellite point. Okay. So pointing of the direction from satellite which is present at the top in space to the sub-satellite which is present at the surface of the Earth is called as nadir direction, NADIR. Nadir direction from the satellite. And for your kind information, the measurement of east, west, north, and south directions are defined for the geographical mapping of Earth. Geographical mapping of Earth. Whereas this zenith direction and nadir direction are for the pointing directions from the sub-satellite to the satellites in space. So these sub-satellite points will be present on the Earth's surface. Okay, zenith point and nadir pointing. So when the satellite sees towards the center of the Earth, pointing a sub-satellite point, so that we call it as nadir direction. And from the sub-satellite point When it sees towards the satellite, we call it as zenith direction. So in simple terms. So for an observer of a satellite standing at a sub-satellite point, the satellite will appear to be directly overhead in the zenith direction. And the zenith and nadir paths would be always opposite along the same path. So the designers of satellite antennas refer the pointing of direction of the satellite antenna beam towards nadir direction. Always, whoever want to design an antenna for a satellite, they take the direction of nadir direction, which is from satellite to sub-satellite point on the Earth's surface. So next is some of the orbital elements that I'm going to define. Is that eccentricity? We all are familiar. Semi-major axis, we all are familiar. Apogee is familiar. Perigee is familiar. Okay, so the orbital elements that are useful to determine the Earth orbiting satellite characteristics are eccentricity E, semi-major axis A, apogee, perigee. All these are already defined. Next is line of apsides. Okay, so the line of apside is the line joining the perigee and apogee through the center of the Earth. So through the center of the Earth, we join perigee and apogee. So that is line of apsides. Next is the ascending node. Is that ascending node is that the point where the orbit crosses the orbital plane going from south to north. From the south pole of the Earth's surface, we move towards the north pole of the Earth's surface. So in that case, the orbit crosses the equatorial plane. Okay, so that point where it crosses is ascending node. In a similar fashion, the point where the orbit crosses the equatorial plane going from north to south, we call it as descending node. Okay, the point where the orbit crosses from the equatorial plane going from north to south. These are the orbital parameters. You can see all those things in a single diagram. Perigee, farthest point. See, this is your center. All right, I'll show you. North pole is represented as N. This is the Earth which is revolving, and this is the satellite which is revolving around the Earth. We have a satellite in an elliptical fashion. The farthest point is your perigee. Sorry, the shortest path is your perigee. The farthest point is your apogee. So the line connecting that to the center of the Earth, or to the line joining the perigee and the apogee through the center of the Earth. So this line, center of the Earth, line joining the apogee and perigee, this is the center of the Earth, is called as line of apsides. And ascending node is that from the south, the line moves towards the point where the orbital crosses the equatorial plane going from south to north. So this is the equatorial plane. So when it crosses is a ascending node. Descending node moving from the orbit moving from north to south. Okay. And then we have a line of nodes. The line of nodes is that the line is a line of nodes. Line joining the ascending node and the descending node to the center of the earth. Angle of inclination is this. This is your theta I is the angle of inclination from the ascending node towards the apogee point. We have the angle of inclination. Then right ascension of ascending node. This is the angle measured between line connecting center of the earth to ascending node and another line from the center of the earth to the inertial point of in space. So this is your right ascension node. Then we have argument of perigee measured as omega. The angle between the ascending node and the perigee. So this is your omega. Okay, so this is your omega. Angle between the ascending node. So this is your ascending node from here to the perigee. So this angle is called as argument of perigee. So in this diagram you can see the north pole and the south pole present in earth. What is the equatorial diameter and what is the polar diameter? Okay, so the equatorial diameter is this measurement from west to east. Okay, is called as equatorial plane. West of the earth to east of the earth, which is longitudinal dimension. Longitudinal measurement. So equatorial diameter. So the equatorial diameter is always 12,756 kilometer. 12,756 kilometer is your equatorial diameter. So whereas the measurement from north pole to south pole, from north pole you can see it is latitude. Okay, latitude, north pole to south pole, which we called as measurement of polar diameter, which is 12,714 kilometer. For the earth, these are the dimension: equatorial diameter and polar diameter. Keep in remembrance, the equatorial diameter is always greater than the polar diameter of earth. So I will stop till here. In the next class we'll see the orbital perturbations. We'll see the orbital perturbations followed by the effects of the Earth's oblateness. Oblateness represents your non-perfect ellipse. Okay, so which is what I'm showing you here, the non-perfectness ellipse. So kindly await, I'll give you the attendance form. Those are filling the attendance form will be given